We'll start. So welcome to everybody and thank you for coming. Today's speaker is Sun-Yong Hwang. Many of you know already. Say it again. The speaker is Anyway, Sun-Yong is a postdoc in the Phys since February this year. And
officially from March.
From March, okay. Well, just a brief introduction. He got his PhD from Korean University in 2011. And then he became a postdoc in Hwang. He came to Palma. And recently, Research Foundation Fellowship. So his talk is for starting. Sun-Yong don't ask the questions.
I mean, the non-commissioned officer, the lieutenant. Okay, and thank you in advance. I'm going to talk about our outside the field of condensed matter physics. Condensed matter, thermoelectricity and insulators is like this insulator which cannot conduct electricity. Within this energy range, carriers cannot tunnel. Insulators are also insulator in the sense that surface there is a propagating state. So actually, this is a really huge, broad area of research. So we cannot cover all today. Not only due to the, more specifically, this two-dimensional topological insulator shows the effect known as quantum spin Hall effect. So we should know what quantum spin Hall effect is, right? So this is the kind of small task today to understand the quantum spin Hall effect. So we better start from the quantum Hall effect to understand the quantum spin Hall effect, right? This is really important effect. In the sense that this shows some topological property in condensed matter and is related to topological invariant. Basically, if you know the quantum Hall effect, this is a filling factor of the quantum Hall effect, quantum Hall conductance. And at this level, we should look at the Berry phase. The concept of Berry phase is really important to understand the topology in condensed matter. Berry phase is kind of a generalized Aharonov-Bohm phase in the magnetic field. You know, if you remember the quantum mechanics, this, the electronic wave function should acquire a phase factor according to the magnetic field flux. So Berry phase is something generalized concept, but it's related to momentum space property of the material. Sorry. And so we talk about the thermoelectric effects afterwards, and finally highlight our recent work published in September. So, Hall effect. We all know this, right? A charged particle in the presence of electromagnetic field should experience the Lorentz force. So, for example, this is the metal strip where the charge carriers are electrons. So suppose the currents are moving in this direction and by convention electrons moving upward, right? And then we apply the magnetic field going through the plane. And then we know due to this term, the electron should deflect to the right side and accumulate on the right side. And then relatively positive charge should accumulate on the left side. So there should be a transverse electric field, right? Transverse electric field, and after some time the equilibrium approaches, and then there should be balancing act between these two forces, so the electron finally move along the straight line again. And from this equilibrium condition, we can define the Hall voltage, which is a Hall voltage proportional to magnetic field and also the dependent on material property. This is a classical Hall effect which we can explain by Lorentz force. And then exact quantization of voltage or Hall resistance is the quantum Hall effect, which was firstly observed in 1980. In their paper, they actually suggested a high accuracy determination of fine structure constant based on this, like I said, exact quantization. So this is a fine structure constant is a fundamental quantity in quantum electrodynamics. So we know this is the speed of light is the constant, and then if we can define the E square of h very accurately, finally we can determine the high accuracy, the alpha. We can define alpha very accurately. So now it can be related to the von Kriching constant, which is the resistance quantum. Okay. And von Kriching won the Nobel Prize just 5 years after this discovery, because it was really an important discovery. So what they observed is actually exactly quantized the Hall resistance in the presence of very high magnetic field at very low temperatures. So given the magnetic field, in this case, when we change the Fermi energy is the energy up to which all energy levels are occupied, okay? So as a function of EF, it shows the plateau. So it's a quantized, so it shows a plateau. And this is, like I said, von Kriching constant. And for example, if you look at this plateau, irrespective of the sample geometry, it shows the exact quantized value. So it's very, important experiment. And also as a function of magnetic field, classically it should be proportional to magnetic field, but at high enough magnetic field, it shows a plateau. So quantum mechanical effect show up here. Okay, we get to this picture again, but now. So the Hall conductance, which is the inverse of this Hall resistance, should be given only in units of E square of h. And this nu is the filling factor, so like I mentioned before. Finally, that's a topological invariant. And this is exact quantization, like 1 part in billion. So it's not like experimental error. It doesn't depend on the sample. And so theorist Laplin says it can't be a coincidence, so there should be something inside. So he, in this very elegant paper, he argued this phenomenon in terms of gauge invariance. This paper is only 2 pages long and just like 3 published references, very original paper. And so let us look at more closely to the quantum Hall problem. So electron in the presence of magnetic field should make a cyclotron orbit, right? But in the radius is quantized in the quantum mechanical sense, but it should make a cyclotron orbit. And if you solve this problem quantum mechanically, this problem is actually like one can solve from the single particle Hamiltonian, and then it can be exactly mapped to simple harmonic oscillator problem. So we know the spectrum, how to solve it. So it can be, spectrum is given this way. So n is quantized value. It's an integer, 0, 1, 2, 3. So it's a gapped state. So it's a gapped state. There is an energy gap, but in quantum Hall case, there should be a propagating edge states. So there is a gapless edge state here. But if you look at the ordinary insulator, it's basically the electrons' wave functions are bound to atomic sites. So it's a bound, the localized. So there is a gap state, but in this case, the gap is given by atomic orbital, like 1s, 2s. But there is gapped states, but there is no gapless states. So here, the question is, what's the difference? What makes this distinction between these two? That's the point where the topology plays the role. Okay. So for example, we know these two are topologically equivalent, right? And a donut and a coffee cup are topologically equivalent. They can transform into each other by continuous deformation, mathematically like homeomorphic or something. But yeah, it can be transformed into each other. But I'm not saying the coffee cup is really transformed into donut. I mean, you understand the continuous. And we can classify this topology by genus 0, genus 1, which is basically the number of holes. Okay. And there is a Gauss-Bonnet theorem, which relates this into Gaussian curvature. The surface integral of Gaussian curvature is related to the genus. Gaussian curvature, for example, sphere has Gaussian curvature 1 over r square. Okay, then so it should be genus 0. And the important point here is that the left-hand side is only, there's no discretized value or no quantized. It's a continuous, the integration and curvature. But finally, the right-hand side is only given the quantized value. So this is basically the topological invariant. So we know this is a number of holes. In condensed matter physics, so there is a curvature. There is a curvature, we call Berry curvature. Like I said, the Berry phase is generalized Aharonov phase, even without magnetic field. There's a Berry curvature in the band structure, and the surface integral of Berry curvature gives some value. That's a topological invariant, really important concept. So something topological, we means in momentum space band structure. So we now consider the famous Su-Schrieffer-Heeger model in one-dimensional polyacetylene, which looks like this, the conjugated polymer. And this thing has related to the Pyre's instability at the Fermi surface, but forget about that. Just consider these states can have, it can exist as two different states. Based on site binding model, so each site can overlap integral given by T. Wave function overlap integral is T, but the first two sides can be stronger coupled, weaker coupled, stronger coupled, but the other case is weaker, stronger, weaker. So these two states actually have same energy, but interestingly, these two actually have a different topology. If you write down some Hamiltonian in the parameter, but forget about the detail anyway. But this is just model, you know, not realistic because they artificially impose the symmetry called chiral symmetry. So this is not realistic, but they showed there should be topological order, topologically distinct, you know. It's a matter of excluding or including the origin, so different topology. The lesson from the Jacob-Rabi model here is that what happens if two different topologies meet? What happens at the boundary? That's the lesson from the Jacob-Rabi model. So here M is like a band gap. So insulating states, but with some different topology. So meet at the boundary, like here. So what happens? They showed there should be, gap should be closed at the boundary. And this closing gap is protected by topology. So at the boundary edge, the gap should be closed anyway. So if you look at the quantum Hall problem again, this quantum Hall states actually has different topology with ordinary insulator, like here, vacuum. So at the boundary edge, there should be gapless edge state. So it's topologically protected. But in ordinary insulated case, it has the same topology, so there is no gap crossing at the surface boundary. It remains as insulating. Okay, so to understand the topology in condensed matter, like I said, it's very important to understand the concept of Berry phase. Before we do that, let us consider again the charged particle in the presence of electromagnetic field again. And we write down the four potential here. A0 corresponds to scalar potential, and A is vector potential. And we know the electric field and magnetic field is given with this potential. And we write down the Lagrangian of this system. So if you can, So to check whether this is a right Lagrangian, one can calculate the Euler-Lagrange equation. And then after some algebra, this exactly gives the, once again, Lorentz force equation. Okay, so this is the right Lagrangian, so we know. And now we calculate the action, which is the time integral of the Lagrangian. Actually, the Euler-Lagrange equation was derived by minimization of the action, if you remember, and it gives the classical path, right? But also quantum mechanically, it can give the wave function phase factor. So it can give it, but quantum mechanically, not only classical paths, but also other allowed paths with different probability amplitude. So now we look at this term and apply it here. And it picks up this term, right, which we call SB. And this is the first order time derivative, so it's finally this term. So this term is finally gives in the action, it gives the line integral of the vector potential. So although we begin with a time integration, it finally is depend on geometric variable. So in this case, this is the example of geometric phase, but we know this is the Aharonov-Bohm effect, right? So now we apply this term to here to get the phase factor, wave function phase factor, and then consider a closed loop, and then line integral of vector potential is the surface integral of curl of A, which is a magnetic field. So this is Stokes theorem, so we know, right? And then the surface integral of magnetic field is magnetic flux. And finally, in quantum mechanics, magnetic flux is also quantized. It should be given in units of flux quantum, which is h over E. So it's finally we can write down this phase factor. So this is Aharonov-Bohm phase. So particle, the wave function in the presence of magnetic field should acquire that phase factor. So it's long before the Berry phase. But like I said, we can generalize this concept of the Aharonov-Bohm phase to Berry phase. Okay, this is the heuristic picture which explains the Berry phase. Like particle is moving along the surface of the sphere, making a closed loop and returning back to the original position. And we tag this particle with two arrows, okay, long and short. These arrows. And suppose this arrow somehow represents the wave function phase, okay. Then we move this particle by parallel transport. There is no rotation in the middle, and make a loop and returning back to original position. There is a phase difference. So we know this is due to the curvature of the sphere, although we use the parallel transport of the state. This is due to purely the curvature. So if the particle moved on the flat surface, there will be no phase difference. You can simply do that, right? So this is simply due to the curvature of this. So in condensed matter, something curved is momentum space. Still, yeah, sounds abstract, but conceptually, that's a momentum space curved. And we have a wave function phase ambiguity like this. We have a freedom to choose phi. This corresponds to actually fixing the initial condition. We can have a different initial condition, but finally the curvature effect should appear same. That is gauging variant finally. So we have freedom, and here whatever the detail of the UK is, we somehow define the Berry connection. Okay. This K is actually the crystal momentum in the blow state. And this phase ambiguity corresponds to this gauge freedom we have. So we define the Berry connection here, and we define the Berry curvature or Berry flux by taking the curve. So if you look at this is very analogous to like a magnetic vector potential and the magnetic field. But there was no magnetic field there, just curvature of the momentum space. So something inside the band structure, okay. So we analogously to Aharonov-Bohm case, we take the line integral of A, but in the momentum space. And then it is by Stokes theorem, the flux of the surface integral flux. And this surface integral flux is finally given by Chern number. This is related to topological invariant Chern number. That Chern number is integer, just integer. Like if you remember, this is quite analogous to the mathematics, the Gauss-Bonnet theorem. But here, the Gaussian curvature is now replaced by Berry curvature, and genus is topological invariant. That is actually something like a Pilling factor. So the message is due to the band structure or the momentum space, there is a different topology appears, and we can relate it some observable quantity to like the Berry curvature to topological invariant. So in summary, whatever it is, we can define the Berry connection, and this is kind of generalized vector potential. So also, this is a kind of a generalized magnetic field. So gauge invariant now is now related to topological invariant. So this is the famous paper by TKNN. they explicitly show that the Hall conductance is given by the topological invariant, like TKNN invariant. As you see, this is a plus. But physically, the filling factor of quantum Hall effect is basically how many completely Landau levels below the Fermi energy. So this is the Hall resistance transverse. I mean, the transverse Hall resistance. Classically, it should be proportional to magnetic field, but as the magnetic field is getting higher, it shows quantized value. So it's a quantized quantum Hall effect. And also, if you see, this is a longitudinal resistance, like transport direction. So whenever the plateau shows up, so it goes down to 0. So there is a ballistic transport along the transport direction. That's the quantum Hall effect. So we know that's from along the boundary edges. The ballistic transport means the transport without resistance, okay? So now if you look at the Landau level spectrum, which is depicted here, right, gapped state. This is actually highly momentum degenerate state because the eigenstate contains the momentum as quantum number, but finally it only depends on n. So many momentum states gives the same energy. So it's highly momentum degenerate states, okay? So if the sample is not clean enough, so there should be many scattering centers and scatters, and then momentum degeneracy should be lifted by scattering, right? So this broadening happens when the sample is not clean enough. So this broadening is kind of a localized state. So by scattering, so it localizes the wave function. So, but still there is these peaked states represent the delocalized states along the edges. And this delocalized states resolution can be resolved very well only if we have a very well separation guaranteed by high magnetic field, right? So that's the reason why we need a very high magnetic field to observe the quantum Hall effect. And also the thermal temperature gives a similar effect for this broadening. So we need a very low temperature. So quantum Hall effect, we need a high magnetic field and low temperature. And so as increasing of V, so there's well resolved, discrete, the Landau level can be below the Fermi energy, so that gives the filling factor of the quantum Hall effect. So far we talk about Hall effect and quantum Hall effect, actually the integer quantum Hall effect. And there is an anomalous Hall effect in the absence of magnetic field but some magnetization and the spin Hall effect, spin accumulation. This is classical and this is quantum mechanical. But we are not going to talk about these. From quantum Hall effect, so we learned somehow very briefly about the Berry curvature. So quantum anomalous Hall effect is zero magnetic field or non-zero Berry flux. So it gives the Hall-like conductance, but experimentally not yet confirmed. So it's suggested by Haldane long time ago, not long time, but 1988. And that's actually the basis of Chern insulator, the topological invariant Chern number. But not yet confirmed. But recently there was a paper just 3 weeks ago, and there was experimental topological Haldane model. So there was a paper about this, and this is a Nature News article explaining this article. So now it's like understand that the key ingredient is not a magnetic field, but rather Berry curvature, right? So we somehow understand that even without magnetic field, there should be some dependent structure gives the like magnetic field-like effect, so it can be understandable. So here in these two cases, this time reversal symmetry is broken. I mean, magnetic field break the time reversal symmetry. Classically, like Coriolis force is like no friction. That's the time reversal symmetry broken. But here, the quantum spin Hall effect, finally our model system, preserves the time reversal symmetry. So it's without magnetic field, but it preserves time reversal symmetry. So it's distinct from quantum anomalous Hall effect and also from the quantum Hall effect. So quantum spin Hall effect, different effect, right? This is a Dirac medalist in 2012, Charlie Kane, Cheng Zhang, and Haldane. They are actually working on the topological insulators. And this it's not going to be surprising one of these people won the Nobel Prize very soon. And this is another story. Like quantum Hall effect, we talk about when the filling factor is just integer. That's an integer quantum Hall effect. But there is another heavy story, fractional quantum Hall effect. This filling factor can be given fractional number, like 1/3. And that's what it is. I mean, there was an experiment, and there was a theory again by Löflin, and these Löflin and these two people won the Nobel Prize for this fractional quantum Hall effect. So in this case, the origin is purely electron-electron interaction. So single particle picture is cannot be applied anymore to this picture. So it's another story. And there will be many interesting topics related to this fractional quantum Hall effect. Okay, now finally we talk about quantum spin Hall effect. Okay. Quantum Hall effect requires, like I said, high magnetic field and low temperature. So if we try to apply this quantum Hall effect for the device, it's not at all good, you know. So it's not good. And like a liquid helium temperature and with like a 15 Tesla magnetic field is not good for application. So theorists thought about, just not even a decade ago, theorists thought about the quantum Hall-like effect, but without magnetic field, but with time reversal symmetry. So it's the latter distinguishes from quantum anomalous Hall effect. So in that case, time reversal symmetry is preserved. Whatever it is, just you can trust me. And so here the spin, purely one-dimensional channel, still like a quantum Hall case, but spin up moves only one direction, and spin down moves the other direction. So spin and momentum are intercorrelated. So this is quantum Hall effect. So quantum Hall case, there is a gabless edge states here, but quantum spin is a spin-dependent edge states. So the motion is dependent on, the spin direction is dependent on the component of the spin, I mean the momentum direction, which way I move. So how about topological protection about quantum spin Hall effect? Quantum Hall case, there is only quantum mechanical channel going only to the forward direction. So whenever it meets the scatter, even if the sample is not clean and there are impurities, it can scatter up, but anyway, it should go forward again. There is no backward way. So quantum Hall case, high magnetic field guarantees the protection of the transport. It's ballistic transport. For quantum spin Hall case, up spin moves this direction, down spin moves this direction. So one can think about like this. So if it meets the scatterer, it can flip the spin and backward scattering. And the backward, that means resistance should be generated. So one can think about, there should be some resistance. So it's not, there will be no protection by impurity scattering. But I didn't explicitly explain, but you know, for spin, to make a spin fluid, there are two ways. One is the clockwise pi rotation, and one is the counterclockwise minus pi rotation. But I didn't explain this, but electron, when it make a 2 pi rotation, it picks up very phase pi very phase, which gives -1 side. This is really, I mean, fascinating property from quantum mechanics. It picks up the half integer spin, picks up the very phase by making the 2 pi rotation. So these two scattering events have a relative phase 2 pi. So probability these should be added quantum mechanically. So these cancels out identically. So still in quantum spin Hall case, I mean, fascinating. Yeah, that is very fascinating. So there's still protection. So ballistic channel along each channel. So like spin up moving this direction and spin down moving that direction, but we don't see each other. That's totally transparent each other. And also the experimentally the interference measurement, scanning tunneling spectroscopy, they revealed that there is no, this channel is totally, I mean, independent. This is like, you know, the anti-refraction coating. You know, this is coating layer, and finally it's like a blue line, land line. It's interfere destructively, so there is no reflection. So it's like that. So there is no backscattering. So far we talk about until quantum spin Hall effect. Like I mentioned, there are many branch of the topological insulator. So I cannot cover all. Actually, this is the example how to realize experimentally the mercury telluride sandwiched between cadmium telluride. Okay, so and the Majorana fermion is another heavy story. So we cannot deal with this today. And the bismuth telluride and the antimony telluride is like you know, this three-dimensional materials. How to realize three-dimensional topological insulators. And this spin-orbit coupling is very important. This is actually now getting, like I said, getting more attention, you know, the star material. And there are many publications recently, right? So on purpose, it's not a mistake. It's so yes. And actually, yeah, TV series Big Bang Theory. Actually, this is quote from the Sheldon Cooper. He's giving this lecture. Who is familiar with the concept of topological insulator? So we take a break for just 1 minute to watch this, just for fun.
Our guest lecturer, Dr. Sheldon Cooper. I was expecting applause. Stunned silence is equally appropriate.
Sorry, here. Okay. Okay, sorry about this. The sound was not loud enough, and finally, it's like you know, the very funny, but topological insulator. Who knows the concept? And everybody raised their hand, and he said, "Don't kid yourselves," and something like that. Okay. Okay, so we just talk about, anyway, the just quantum spin Hall effect very briefly, so I couldn't deliver many things, and there are many books and review papers. So if you just Google the topological insulator, you can also find out many lecture notes and the video lectures given by like Charlie Kane and Su-Cheng Zhang. And so if you want to learn, there are ways. Okay. So now we talk about the thermoelectric effects. We know the voltage difference generates electric current, right? Like with batteries. And G is the electrical conductance. And also, the temperature difference generates the heat flow. It's like entropic motion, right? So, the K is the thermal conductance. So we know this. But also, the different temperature across the thermoelectric material, it can generate the electricity. It's a Seebeck effect. So we add this term here to the electric current. And also the electric field across the two material junction, the heat can be observed and expelled. This is a Peltier effect. So we also add this term here. So there is a material which we want to investigate. And we drive this material by not only the electric field, voltage, but also with the temperature. The thermoelectric effects are basically the conversion from temperature difference to voltage difference, or vice versa. And then this is basically the thermoelectric effect. Of course, there are other effects than these two effects, but today just think about these two effects for our work. And quantum mechanically, and this conversion efficiency, which is basically very limited, can be very large in quantum system. So for example, this is the temperature to voltage, conversion by quantified by this Seebeck coefficient or thermal power derived from the open circuit condition. So that can be very large in small system due to some quantum mechanical nature. So there are many motivations in investigating this nanoscale thermoelectricity and control the heat and high efficiency heat engine, even approaching to the cardinal limit and the technological aspect. And also in relation to topological insulators, there was a study about the topological family of material can be very, the figure of merit can be very high. This figure of merit is a quantity which quantifies the efficiency, but it's usually very lower than the 1, but if it's bigger than 1, it's very good. So it already shows a very high value. So this is dimensionless figure of merit. So it's electrical conductivity and electronic part of the thermal conductivity and phonon contribution of thermal conductivity. It's a lattice vibration. So the reason why we cannot increase these values, like for example, the electric conductor is also generally the good thermal conductor. So it's very difficult to increase this. But in quantum mechanically, we can somehow use the separate the energy-dependent density of states, or the material or the nanostructuring. So there are many schemes to increase this conversion efficiency. The first step may be the decrease the phonon contribution. So in any way, suppress the phonon contribution of the thermal conductivity can be a good way to do. Actually, this paper shows in quantum spin-hole case, at low temperatures, the phonon contribution can be neglected. So in our model, we finally neglect the phonon contribution. I showed here I present only up to the linear regime. linear V, linear T. But in many cases, the system depends non-linearly. So V square, T square terms should be very important. Like, showing the rectification effects and so on. So we need actually the nonlinear theory. So, and David and Rosa already made a very nice nonlinear theory for this work. So, nonlinear scattering theory. So, finally, we could apply this formalism to our system. So, this is a quantum spin Hall system where a spinor moves along the blue lines and downspin moves along the red lines. And we consider a two-terminal. So we drive by voltage and temperature difference. And we just consider a normal metal case. Normal metal means not ferromagnetic. So there is a priori no spin imbalance. But finally, the aim is to generate some spin imbalance, so spin polarization. So only by using quantum spin Hall effect. So this is try to make some combine the effect of quantum spin Hall effect from the thermoelectric perspective. So we put a structure, gate control of a structure here. So it's like a quantum dot. And this upper channel can, scatter through this channel, through this structure, and lower channel also. But here the gamma is basically the energy scale from the uncertainty principle, and this gamma sets the tunneling rate. So if the large gamma means more frequent tunneling rate because the delta t is short and dwelling time is very short. So we use the formalism here. This is a spin resolved current. The sigma means the spin component. So this A contains scattering property through this structure. Okay, scattering matrix relates the incoming waves to outgoing waves of the electron. So here is a scattering properties included. In heat case, the E is replaced by the energy carried by the electron. So we use this formalism and then determine the total flux and the spin polarized flux. And since we consider two driving forces, voltage and temperature, so technically we need to consider distinguish these two. This is technical detail, like particle injectivity and entropy consideration. But basically, if you look at this, for thermal bias case, the charge can move both directions due to thermal broadening of the Fermi function. And here, this A matrix scattering property also depends on the potential U. So we should determine the potential response, but up to nonlinear regime. So in the linear response, the equilibrium potential will be enough, but nonlinear regime, if the charges are going inside the sample to redistribute the potential. So we model this up to the linear order of the driving field here, and we solve the Poisson equation. And this is a long paper, so there are many things to discuss, but if you just highlight our work, pure spin polarized currents can be generated by thermoelectric combination. The thermoelectricity and quantum spin Hall effect can make a spin polarization. Pure spin polarization, even the total flux is zero, only spin polarized and heat flows. So it's like a temperature to voltage conversion, which is a Seebeck effect. And then this is voltage to temperature conversion, which is a Peltier effect. So spin polarized currents is given this way, so generated thermal gradient. So temperature difference generates electric spin polarized current, pure spin current. and the voltage difference generates the spin polarized heat. But if you see this eta is the coupling asymmetry, which means here this dot should be more strongly coupled to the upper or lower edges. There is, if there is symmetric, there is no effect. So this is another important factor, and also this is, quantifies the interaction. So we need the interaction to observe this effect, and also this is only up to only from the second order. So it's a nonlinear effect. Linear order, whatever the case, we cannot observe the spin polarized current. So we can highlight our work this way. So it's a combination of spin Hall effect. We don't use any ferromagnets, so there was no a priori spin imbalance, but finally we could make a spin imbalance through the quantum spin Hall effect and thermoelectric effect. So thank you for your attention.
Okay, time for questions.
In your model, is there any mechanism that sets a preference in spin direction? And, if I understood correctly, you don't have magnetic field.
Yeah, in this case, we don't need a magnetic field. There is only by driving. So, for example, so here, Fermi level is here. The electrons are filled up to Fermi energy. So this is just ballistic transport channel. So with the Fermi energy, it moves. Spin up, moves this channel. And spin down with this energy, moves this channel. So that is the reason why we need this kind of structure, because there cannot be any, the spin imbalance if you use the normal method, because there would be the same portion of the spin up and spin down.
They are arbitrary choice, no? It can be up or down in any...
Actually, this spin Hall effect has a very, well-defined spin direction of the... You mean the injection?
No, my question is about when you say that temperature difference creates a spin current.
Yes.
In what, I think we discussed it sometime. What spin direction? What is telling you creates a spin current in a given spin?
In this case, spin up is perpendicular to the plane. Yeah, this is perpendicular to the plane, up spin, and the other spin is spin down. So
it's in this specific...
Yeah, this is a two-dimensional sample, and the spin up moves this direction, spin down moves this direction, the perpendicular to the plane.
I have a question about this very curvature.
Yes.
So you emphasize the, let's say, the analogies with a real magnetic field, but there might be some differences, right? Formation of Landau levels, or
there is very curvature makes no Landau level. So Chern insulator in this case is the example of no Landau level. If you see. Actually, this is the original title of the Haldane model. So this is model for quantum Hall effect without Landau level. So it's without Landau level, without magnetic field, but in this case, still time reversal symmetry is broken. Actually, this is model, Haldane used the model, graphene model. So actually, long before graphene was in the boom, so he chose this model. So in this system, no Landau level, but yeah, that can be a difference, but anyway, time reversal symmetry is broken, like a real magnetic field, but yeah, not really.
okay.
Yes. And other reciprocal relations in the thermoelectric effect you show. Have you studied that, or if they are fulfilled, or?
You mean like in terms of quantum thermodynamics?
Yeah, so the coefficients.
Yeah, like Onsaga in the linear regime, like Onsaga-Kashima division, something. Yeah.
I mean, in this particular case. If they are fulfilled or
Linear regime, they should be fulfilled. We are sure. But non-linear regime, no. Even quantum Hall case, we already previous work, we show the non-linear regime, the Onsaga Cashmere will be broken. So it's a, you mean, yeah. Any other questions?
What's the difference between the edge states of the system and the Majoranas?
Majorana is actually, you mean the 1D topological system? Su-Schrieffer-Heeger.
Because this system has a Dirac-like expression around weight number 0. For this reason, it will be Majorana is the space in the sense of the statistical sense.
So like I said, Majorana is another heavy topic I cannot deal with. That also actually, personally, I had very bad memory with the Majorana permits. I worked on several months and no output before. Anyway, yeah, Majorana is but basically the in proximity to superconductor and the magnetic field and spin-orbit coupling of the wire. So in this case, also the edge, there is the 1D nanowire at the edges, Majorana should appear, right? So in this case, also like a dimensional, like a 2D case has a one-dimensional edge channel. Majorana is a one-dimensional channel and edge channel. But it's different from Su-Schrieffer-Heeger model in 1D topological because there is not real or just model system. But Majorana is there is experiments and verification of the Majorana. So yeah, boundary effect, yeah. In the spirit, yeah, that's also the case for Majorana.
Okay, so I propose to thanks everybody.